Okay, this is example program, Unit E2, page 8. The last page of the Unit E2. Let's take a look at the example program here. The fluid dynamic characteristics of an airplane flying 240 miles per hour at 10,000 feet, it looks like this is a cruising condition. These are to be investigated with the aid of a 1/20 scale test model. If the model tests are to be performed in a wind tunnel using standard air, which is sea level standard property, what is the required air velocity in the wind tunnel testing? Is this a realistic velocity? Let's take a look. By the way, before we begin, this is massively open-ended program. So whatever I say here may not be the only solution. You are going to find out your own solution later on when you become senior student. This is very, very typical condition of your senior design project. You are going to design an airplane, and then happen to be, let's imagine your airplane cruising condition is 240 miles per hour at 10,000 feet. Then somehow your team wants to test it in a wind tunnel, okay? Then our wind tunnel is so small, so you have to shrink your airplane into 1/20 scale. It's a fairly small airplane. So you stick that airplane into the wind tunnel we have, then, hey, wait a minute, what is the wind tunnel test section speed? Oh, let's figure it out. So imagine that's the situation, okay? So first of all, the typical choice for that is a Reynolds number. So you want to set the Reynolds number of your actual airplane flight condition against your Reynolds number of your wind tunnel testing. You want to make it equal to each other, okay? So let's say Reynolds number, let's say prototype P is equal to Reynolds number of the model. You want to set that for your wind tunnel testing. Usually it's impossible, but let's take a look at it, okay? So let's list the conditions for prototype. So prototype, your actual airplane. Flight condition is 240 miles per hour. Pretty high speed. Density and viscosity of the prototype. In other words, your flight condition is 10,000 feet. So if you're using standard atmosphere at 10,000 feet altitude, density will be 1.756 times 10 to the minus 3 slugs per cubic foot. This one is 3.534 times 10 to the minus 7 pounds second feet squared. Keep in mind, those are the standard value of 10,000 feet altitude. Well, perhaps your design team wanted to design and build an airplane which is capable of flying 240 miles per hour at the 10,000 feet altitude. This is probably typical cruising condition of your design. Sure, I understand that. So let's take a look at the model. In other words, you want to test your airplane in wind tunnel. Wind tunnel is usually limited facility, okay? So for model, density and viscosity. Wind tunnel is usually located at sea level. Now at the Prescott campus, wind tunnel is located at 5,000 feet altitude, but usually it's sea level. So let's use sea level value here. So density 2.377 times 10 to minus 3 slugs per per cubic foot. Viscosity is 3.737 times 10 to the minus 7 pounds second per square foot. Those are the standard sea level. This is a test condition of your wind tunnel, usually standard sea level. Okay? So your purpose here is, what is the wind tunnel test section airspeed set up? So how fast should I go for testing in order to represent the similar condition of that? So should I go for 240 miles per hour? It's probably a dumb question because we know the answer is no. Okay? One more thing, this is, model is 1/12 scale. It's a much smaller size than actual size. So for a smaller size model, should I go for 240 miles per hour for testing? No, I don't think so. So what is it? So if you want to match up the Reynolds number between prototype and model, what is the BM? So that's just a kind of game, okay? In order to satisfy Reynolds number prototype is equal to Reynolds number of the model. It really means that the density of prototype times velocity of prototype multiplied by length scale. This is length scale, characteristic length of prototype divided by viscosity of prototype must be exactly equal to density of the model test condition, velocity of the model wind tunnel. This is again length scale of the model divided by viscosity of the model. Now, common mistake is, obviously this is 1/20. This is 1. Because you're using smaller model, right? So let's be careful about that. So from here, let's solve this one for BM equal to. So this is the wind tunnel test section airspeed you need, which is velocity of prototype, which is, we know this is 240. Multiplied by rho of prototype divided by rho of model, multiplied by viscosity of model divided by viscosity of prototype. This is flip-flop, because this and that. Flip-flop, okay? Let's be careful. This is the length scale of the prototype divided by length scale of the model. So let's just prime here. This is going to be 240 miles per hour times 1.756 times 10 to minus 3 divided by 2.377 times 10 to minus 3. Now units are slugs per cubic foot, but you're taking ratio, so I'm not going to even write the units. Viscosity, model viscosity, 3.737 times 10 to minus 7. Prototype viscosity, 3.534 times 10 to minus 7. Not much difference. By the way, units pound second per feet square, but these are ratio, so I'm not going to even write units. Looks like it's not much big deal, not much change. Obviously, this is much bigger as a density. Viscosity doesn't change much. Yeah, sure, okay. This one is 1/12. Right? This is much smaller, much bigger. If you seriously, you pick up your calculator and punch those numbers in, you're going to have that you're not going to believe your eyes. So wind tunnel test guy in your team says, hey dude, we have to test this model in our wind tunnel based on my calculations, 3,750 miles per hour. That's the wind tunnel test section airspeed. Then if you're a team lead, your reaction is, I don't think so. What are you talking about? I don't think so. I guess you probably made a mistake. Then you go back and quickly and check everything. Well, yeah, this is right. In order to satisfy the same Reynolds number in your wind tunnel test section, this is what you need. Can we do this? Forget it. Impossible. Who can do this? Nobody. This is like Mach 5. 3,000 miles per hour of a wind tunnel? That's insane. So, I guess you're saying, what? I'm not kidding. This is what you're going to end up being, when you become senior student, trying to determine the wind tunnel test condition. Then if you want to satisfy the similarity in terms of Reynolds number for this condition in the wind tunnel test using 1/12 scale model, this is what you need. And then it's impossible to do. Now the real discussion begins here in your senior year. So what? Well, we have to do some kind of wind tunnel test. Forget about this. So tons of discussion comes up. Well, we can go all the way back to this condition saying, okay, who actually said you need to test this condition? This is really high speed anyways, 10,000 altitude. Why do we need to test it? What is the purpose of the test? Well, it's not clear. Okay, so what about you want to test your wing because your airplane's design is kind of unique on your wing. Our wing design is high lift wing, so it's going to help you take off and land fairly short distance. So let's just change this test condition in takeoff and landing, which is much lower speed. So let's focus on the wind tunnel testing to check to see if the wing design is effective or not. Then if so, you don't have to model the entire airplane in a smaller scale. You can just pick up just a portion of the wing in bigger scale. Instead of 1/12, you can test it like 1/2. This one becomes much smaller, so all of a sudden this velocity goes down. Maybe instead of 3,000, you're talking now about 700, 800 miles per hour. Still high, but it's much more reasonable. And then suppose if you're testing much lower speed, let's say not the 240 miles per hour cruising condition, you are testing takeoff, let's say like 100 miles per hour takeoff condition. Then you're using much bigger scale, not the entire airplane, but the section of the wing kind of thing. This can become much reasonable velocity, right? Okay. Well, obviously you can think about, can we somehow compress the air in the wind tunnel? Yes, we can. I think NASA has a transonic wind tunnel test facility which is capable to compress the air within, but it's very expensive and usually it's not a reasonable choice for a student project. Okay? So you have lots of solutions, range of solutions. Super dumb to super smart solutions. Okay, so it's not like a right and wrong kind of situation. So as a team, you get together, discuss about, okay, what about this, what about that? Then you're going to range from reasonable solution to excellent yet we cannot afford type of solution, which is, you can basically do the engineering. It's a real engineering, yes. This is the situation, so what? Do we have any cure for this? Okay. So like I said, this is an open-ended question. And then I can guarantee you're going to encounter this kind of problem when you become senior student doing airplane design or spacecraft design. What do you do? Okay. So let's be ready for that kind of real engineering in senior year. Okay? Stop here.